yellow cards and then the red card. Like, I think I have 2 yellow cards.
What happens if you get
But I didn't cuss at other people. I just cussed at like the board because I didn't understand.
What happens if you get a red card?
You have to go to OCR.
What?
Okay.
Who do you have?
All right, so quit wasting your time. Limited number of minutes in the class. This is all you got. So with this, electron configurations, you got the arrow diagram. So once again, you've got that periodic table, yet another copy of another periodic table. But I wanted to pass this one out to you to remind you that this is the exact reference sheet that I'm going to give you on the test. By the time we get to the chapter 12 test, you'll know what all 3 different things are. But I will still give you this one, even though this is from chapter 11. You still don't have to memorize it. I just want you to be able to use it. So we would use this diagram to figure out the electron configuration. Sodium is 1s2, 2s2, 2p, 6, and then
3s1.
3s1. There we go. Sulfur is going to be 1s2, 2s2, 2p, 6, 3s2, 3p, 4. Good, nice. You might pass the test. Okay, maybe not, but we might. What are we doing? Second big thing that we need to focus on for this chapter, and to kind of layer these skills up that we've been working on, is the concept of valence electrons. We've already mentioned this one, but just in case you didn't get it yet, here's another chance. What's a valence electron, and why do we care about them?
The last 2.
Yeah. So valence electrons are the ones in the highest energy level, and they are both S and P electrons in the highest energy level. They're never D or F because of electron overlap or orbital overlap. They'll never have a D orbital be the highest one. So they're always S and P. The reason why they care is that when we're talking about bonding, the actual reaction stuff, what's involved in doing a chemical reaction, it's the valence electrons. It's never the inside ones. So this is why we kind of keep making such a big deal out of valence electrons. Why do we care? Because these are the ones that are actually involved in the bonding. Nothing else is, just the valence electrons. So being able to identify which ones are valence and how many there are is kind of the key component here. So in sodium, what's our valence electrons? Okay, highest energy level is energy level 3. So we only have currently 1. So the way I would do it is just do something like that. That's my valence electron. In this case, I just have 1 valence electron. How about in sulfur?
3p.
Okay, this is the highest sub-level, but it's not the highest energy level.
3p.
Okay, these all count. And that's the important thing. That's the thing that students do that all the time, when they want to say, oh, it's just 4 valence electrons. It's not. Highest energy level includes the S and the P sublevel, so it's everything together. So in this case, what's our total number of valence electrons that we have? 6. Okay, so that's a key thing. And again, that's a really common mistake that students make, is that they forget to include those S electrons. But that's why it's both of them together, the sum total of electrons in the S and P orbitals, or the S and P sublevel, however you want to say that. So far, so good? Okay, so in bonding, key idea. So one of the key ideas here is that in bonding, there's a special stability to having a full or empty valence shell. Don't know why, it's just what it is. That's just how the world works, that when it's perfectly full, that valence shell, then that means it's happy, it's more stable. Certain elements are already like that, where they start off life as having a full valence shell. They're called noble gases. Every noble gas ends in a P6. They're already full. That's why they don't react. They don't need to gain any electrons. They don't need to lose any electrons. They're already stable, other than helium, which is too small. Only has S2. All those other ones over there all end in 2p6, 3p6, or 4p6, something along those lines. They're all already full. Everything else isn't. And either wants to gain a couple to fill it up, or get rid of a couple to empty it out, or share a couple to kind of pretend like they're full or empty. And so when we're trying to do bonding, it's kind of important to know what you've got and then what you need to get gain or lose to kind of fill them up. So with this one, what's the magic number going to be? If you see in this valence shell, what would be perfectly stable? How many total?
2 more.
2 more, but what's the total number that would be in the valence shell?
3s2,
3s2, 3p6, right? So how many valence electrons do they have when they're stable? 8. Magic number is 8. So magic number is 8. So in that last shell, they want to have 8 electrons, if at all possible. Other than hydrogen and helium, some of the little ones, they're a little different. But they want to have 8 because, again, that means that they're at that weird little stability point. Once they've gained that 1 electron, become an ion, then they're cool. They're done. They don't have to do anything else. They might stick to other stuff because they're charged, but they don't need to do anything to become stable. It's kind of a weird thing that they do. So the magic number, you'll hear me talk about this a lot, is 8. So far, so good? Okay, so, all right. I'm gonna erase this. You can kind of keep doing your table straight down below. So we can kind of think about some different ways to represent this to help us figure out how many valence electrons there are, how they're kind of distributed, what they're going to do to gain or lose. So this is one way to represent the electrons in an atom. Here's another way. Same stuff written in a different way. This is called a shell diagram. Again, you can kind of just keep continuing down below in your table. Because the stuff about valence electrons is all kind of a part of the same thing. But shell diagrams, a way for us to think about, all right, how many electrons does it need to gain or lose to get to that magic number of 8? So what I'm going to do is I'm going to take this diagram, I'm going to represent it kind of even more abstractly. Some students like the shell diagram, some students like electron configurations. 2 different ways to represent the same thing. A lot of times you can just choose. So here's what a shell diagram looks like. Don't draw this part yet. So Bohr's model of the atom, nucleus, energy levels like that. We could talk about how many electrons went in the different energy levels. So a shell diagram is like a miniature version of this. Without drawing the whole big bullseye, I'm going to draw, and you've seen me draw something like this before, like that. Nucleus, first energy level, second energy level, third energy level. Just drawing a slice of it. Anyone not sure what I'm drawing, how I'm kind of doing this? I'm just drawing a slice of the energy levels. So for sodium, nucleus, first, second, third, energy levels. Again, just sort of some random sort of curves to make first, second, third. How many electrons are in the first energy level?
2.
Right? 1s, 2. So I'm literally just going to write the number 2 on top of that. Or label it next to it somewhere like that. 8. A second energy level
8.
is 8. Those 2 plus those 6. Those are all in the second energy level. They all start with that energy level number 2. So there's 8. 1. And then 1. So this kind of is a way to summarize that electron configuration, where you can kind of really see that magic number piece kind of really starts to pop up. Oh, here's my valence shell. It has 1 in it, and the previous one's full. It's got 8 in it. So that's a stable shell. This valence shell is definitely not stable. It's just another way to picture the same kind of information. Okay, the same thing for sulfur.
Getting rid of that increases the charge. Right?
Mm-hmm.
2.
Okay, first energy level,
2,
2 and always 2. If it's got anything in it, I'll have 1 or 2.
8.
And then there's our second energy level,
8 and 6.
8. And then this one has 6, exactly.
You
So again,
add 2, 'cause
right, you got it, totally, Kai. So this is one of those things where it kind of makes it easier to see that magic number and kind of what is it going to need to do. So this one would really happily get rid of this electron to have an outside full energy level, empty it out. This one is going to empty it out or fill it up. Fill it up. It's going to gain some electrons to it. So this is kind of that next part. Sometimes these shell diagrams make it a little bit easier to see kind of how they become ions. So what is this one going to want to do to become an ion? It's going to want to get rid of it, right? It's going to want to. If this one can do that, it's going to do this. And what is this one going to want to do? It's going to add 2. For them to become stable, again, this is an ion. This is an ion now. The green was their original kind of setup. And then the red is now what they are afterwards when they become an ion. Have they gained some or lost some? It's kind of like a before and after picture. Okay, shell diagrams. It's an easy way to see this. I'm going to represent this even more abstractly than this. Because really, I don't care about anything but the valence shell. The only ones I care about is this last shell. It's not the other ones. Those inner ones are never going to change. They're kind of shielded, called core electrons. They don't really do anything for chemistry. They're just there. Just the outside layer is the one that we really care about. So there's a last way that we can draw these that's even simpler yet than this. Once you kind of get used to this, it's like getting more and more abstract. It's kind of weird. These things are called dot diagrams. This is the third thing. We're going to use these a bunch through the rest of this chapter, dot diagrams. But they're based on electron configurations, and then they're based on that shell diagram. And then we're going to kind of wrap them up finally as a dot diagram. It's like the most distilled version of just the basic information we need. So here we go. This is what sodium atom looks like. Sodium atom. How many electrons were in the outside energy level at the beginning? Sodium atom. 1. Again, that's its original format, sodium atom. We put the dot over here on the right. I'll show you what the rules are for putting the dots on in a second, because there was one dot for that one valence electron. I don't care about the core electrons at all. Yes, you have to put the symbol for it, because I need to know what element it was. Otherwise, it's just a dot. What's that? I don't know. Sodium. Really? Sure. Maybe it's lithium. Hydrogen? I don't know. So we've got to put the symbol in there. And then the one dot for the one valence electron. What is it after, now that it's becoming an ion? Is this valence shell full or empty? It's empty, right? So to show the after, we do a couple little things to make it look a little bit different. So the after starts a couple of different ways. Still do the sodium in there. Sodium ion. So this would be the ion version of it. Does it have any dots around it? Is there anything in the valence shell after it becomes an ion? No, this one's gone. Does that make sense? Valence shell is now empty. So we actually put no more dots on it. It's given it away. It's like after, it's already gone. So to indicate that we didn't just screw it up, we will use square brackets. Square brackets indicate ions. And then we will write the resulting charge afterwards outside that square bracket. So this is what sodium ion looks like. This is the dot diagram for sodium ion. There's no dots left because it's given it away. When you give away something negative, you become positive. Kind of a metaphor for that. It's like giving away an electron, right? You guys know math, but that becomes that, right? When you do the double negative kind of thing, it's weird how this works. So sodium atom has the one dot to it. Sodium ion does not have any dots because they're already been given out. But we represent it with a square bracket. Say, hey, this is an ion. This isn't its original form. We're going to do the same thing for sulfur. So sulfur. What is sulfur atom going to look like?
6 dots.
This is the atom portion of it.
Do you put 6 dots around it?
Okay, valence dots. So how many valence electrons are there?
6.
There were 6 to begin with. So here's how we put them out there. And this is kind of a little bit weird. You guys remember from orbital diagrams? I'm going to do this as an orbital diagram really quick. 3s2, 3p4. It kind of looked like this. So we had 3s1, 3s2, 3p1, 2, 3, 4, like that, right? So those guys are paired, those guys are paired, and those guys were single. That's the orbital diagram from this. We're going to kind of represent it the same way. You'll get used to this in a second. So this kind of, clock directions, 12, 6. I guess this would be 3 and then 9. No, 3 and 9. Sorry, I did it backwards I'm reverse. So typically this spot right here is where we do the s electrons. So we would do dot, dot. Those guys are paired up. These other 3 corners, the 12, 9, and 6, is kind of where we do the p orbitals, where their dots go. So we would have a pair, a single, and a single. Been a while. But we kind of do them at the corners like that is where we do them. We pair them up if we can. But again, they're going to be singles. There's going to be that stinky roommate piece. So I kind of think of it as the S apartment, P apartments like that kind of spread around there. It's not a big deal. The only thing I just don't want you to do, please don't do this, is to do 1, 2, 3, 4, 5, 6. Don't just do like a random circle, or don't just do them like, seen that one? I've seen, I've seen a couple little random sorts of things. So It's not a huge deal. I'm more looking for the right kind of things, but you set them up like this, it makes it a little bit easier to figure out kind of what they're going to do when they become ions. Question, Ruby? Like, why are the two here and the one single there?
Why are those singles in that?
Yeah, no, just have it. That's kind of how they sort of decided to fill them around. Like, this is the P1, P2, P3. And even as we get later on, we're going to move them around anyway.
You do two dots, but you match those two up.
Like these two, and then do a single like that or something. That's fine. Don't care. Yeah, not entirely. Don't care. The one thing I would not like you to do, please don't do this. That shows everybody has roommates. That's what you're asking?
Yeah, why can't
Okay, why can't you do that? Because that would be
you? Oh, I understand.
that. And they're not going to do this. They're going to fill out every spot first before they go back and take roommates. Does that make sense? Okay. So that one, and again, it's not a huge deal, but this is a little better. This is perfection right here. Close enough. All right. So sulfur atom looks like that. It's got its 6 valence electrons, S. We got our P electrons out here. When it becomes an ion, what does it want to do?
Add.
It's going to get all 8 in there, right? So is that valence shell going to be full or empty? Full. And you have to draw it that way. 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be sulfur ion. Again, this is the after. So sulfur atom has 6. Sulfur ion has 8. What else do we need because it's an ion?
The parentheses.
Need the square parentheses, brackets,
With 2 minus on the outside.
and then a charge. So it's going to be this. You always put brackets around those as ions. This shows me that you've gained or lost some electrons. And then what's its charge going to be?
2 minus. Minus.
It gained 1 here and it gained another one there. So if you get 2 more negative charges, you become a -2 ion. And that's where that charge comes from.
Oh my god.
Kind of all comes back together. Weird. Like, nope, lost. Done. We'll come around here. I'll get you a little bit. So far, so good? Okay. So, on the lab that we're going to do today, you're going to be kind of working with some different atoms to try to figure out how they form bonds. Do they gain electrons or lose electrons? Kind of like this sort of thing. Practice writing electron configurations and shell diagrams and dot diagrams to kind of figure out what those are. And then start to put them together to form some molecules. So if you don't have the lab up in front of you, please get that out and kind of take a look at it. So make sure there's 2 pages to it. You should have 2 sheets.
Should we put our machine notebooks on?
No, leave it out because you may want those references. Just have them on top, kind of. What? No, if you'd been in class on time, you'd already have these. Seriously, there's that. Do you need an extra copy of your drawing table? I have one of those.
I have one of those.
Do you have one of these still? Yes. All right. So, first things first. Please put your name up here because you're going to forget because it doesn't have a name on there. This is going to go in your notebook, but in case these tend to fall out and disappear, put your name up there. Second thing to put up there, please, is write 11B in the corner. Just write now while I think about it. Put your name on there and then write 11B. This goes in your notebook. Sorry, 12B. 12, not 11, 12. Sorry. Yeah, 12B. 12B, I know, I'm epically failing. 12. Thank you. Chapter standard. Welcome back, Cody.
Okay.
I'm just going to call you Kenny from now on. Guys, your time. Minutes are literally, you're going to be sad. No, you're not. You're going to be super stoked, but you're going to run out of time. So, minutes. So with this is the page that you start on. It says electron configurations on the front. We've already done 2 of these because sulfur and sodium are both in this list. But you're going to go through this process. We're going to go figure out what the electron configuration is. Make sure to circle or box or underline or something. Use different color, I don't care. But do something to identify what the valence electrons are. Practice that skill. Next thing is to do that simple little shell diagram with the little curves to kind of identify what's what. And then for the dot diagrams, these are the dot diagrams for the atoms, not the ions. So if you want to write the word atom up in there, that's what I'm looking for, not the ions. Yes, sir?
So we don't have to do before or after in the show? Or
No, you don't. Nope, you can just do the original starting parts. So this is all kind of for the atoms version of it, not the ions yet. So you'll go through and practice these. These atoms, all of these elements, are the ones that are used in part 2 of the lab. So you're setting yourself up for the stuff that you need in the other half of it, where you're going to build models of how these things react together. So let me kind of show you an example of what this looks like when we start to build them together. So when you're building them, here's the second page. Please start on this side, where it says sodium and chlorine on there. It's the second sheet. Okay. Do not start on this side, where it says BEF2. This is the second half of that. Please do not start here. Start on that part right there. Okay, so just so you know where to start this, I had some students in the last period start on the wrong section of it. God, this is hard, so you're starting in the middle. Start with the easier ones. Okay, the directions are down here. It's kind of in a weird spot. This is at the end of the first page. Create Froot loop atom models for each of the compounds. Kind of in a weird spot, just the way that, like I said, the document's formatted. But the directions are in here, and I'll show you kind of what this looks like. So, all right. So this first model, what we're going to do, we need to build a model that has one sodium atom and one chlorine atom. That's what this first column is telling you. This one down here, you're going to build a model that has 2 different chlorine atoms. So it tells you kind of how many of each type to each model to build. I will show you how to do this illustration of the chemical bond, kind of like what we just drew. Type of bond, you're going to tell me if it's ionic or covalent, and then you're going to tell me what the final formula is. And some of these, like there's already some information that's kind of filled in, just depending on what it is. So look at the document before you ask questions. There may be enough information there for you to do what you need to do. You're like, I don't know what kind of bond this is. Well, it says covalent. Oh. How many fluorines is in there? I don't know. Maybe 2. Right? So again, there's information in there. So what you're going to do is build these models using that. You got the big bullseye that's on there? Our first element is sodium and chlorine. So here's what this looks like. I'm going to study for this. What's our electron configuration for sodium? What's our shell diagram for sodium? You can think of it that way if you want to. Okay, so there's 1s2. Okay. 2s2. Okay, there's 1, 2. Here's our 2p6, 3, 4, and then 5, 6. There we go.
What? Heck?
No,
I don't have enough of the same color.
No, but like, I don't understand.
No, it's because they're 2s, so it's the second.
1s2.
And the 3s are the third.
Oh, okay.
Thank you.
Thank you, Kai.
Thank you, Kai. Fantastic.
And then 3s1.
And then what was the last part?
3s1.
3s1. So when you're building these, something along those lines, you're literally just building a version of the shell diagram. 2 in the first level, then there's 8 in the second level, but they're always in pairs, like the dot diagrams are. And then there's 1 in the third energy level. That's what sodium would look like. We good so far? Okay. Chlorine, which is the second one that you need to do. Chlorine ends in a 3p5. You can kind of see it up there. 1s2, 2s2, 2p6, 3s2, 3p5. So it's got, in that last particular one that it's got, there's the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. There's 11, 12, 13, 14, 15, 16, 17. There you go. There's chlorine. Looks like that. Chlorine kind of looks like that. And I've got a single Froot loop down here. We're doing so far. We're doing okay?
Why does it say cut out each ring?
You don't have to cut them out. I just do them on paper, making our lives easier. So the way that this will work in this lab is that this is meant to be done with partners and Froot loops. So one of you will build the sodium, one of you will build the chlorine, and then kind of set the models side by side. What do we need to do? Do we need to transfer electrons, literally pick up a Froot loop and move it to the other diagram? Will that make everybody happy with a magic number of 8? Or, and we have not talked about this yet, so when you get to this one, you need to ask this question. Do they move together and kind of shake hands? And do they need to share a pair of electrons to make something happy? And again, that's the part we haven't done yet. We've started with ionic, and so I want you to kind of practice. The first two that you've got are going to be ionic bonds. With this one, what is it going to want to do to be happy? Chlorine. It's going to want to gain an electron down here. So where would it get it from? I don't know, maybe sodium would give it up, and I'm just going to use different colors for mine. What I would suggest that you guys do is you build these models in this particular activity. Whoever does the metal, do it in like the warm colors of Cheerios, like red, orange, and yellow. And then whoever does the non-metal, do it in the cool colors, like, not Cheerios, Froot Loops, like blue, green, and purple. So you can really kind of tell where those electrons started their lives. It just makes it easier for you to see it, which is why I do this lab with Froot Loops and not with Cheerios. So you can actually kind of see where the original electron source was. Again, you do not need to do them all in the same color, because I don't think we have enough. You got to work with partners and all this. When you get to the spot to try to figure out how to draw these, like the representation of the chemical bond, ask me before you draw this. Show me what it looks like on paper, and then I'll kind of come around group by group, and then you can ask around in other groups that have already had me talk to them to see what this looks like on paper. It is not like just representing the Cheerios. It's going to be using those square brackets like we did for the ionic ones. As we get to covalent, it looks even a little different from that. Yeah, it's actually a little bit easier. So again, when you get to the spot where you're trying to build this, please call me over, because if I just try to do it right now, it's just going to go over most of your heads anyway. Does that make sense? Don't draw these without asking me for help. Yeah, Ruby? Okay, do that part first. So Ruby just asked. Okay, hold on, I'm going to dump out my Cheerios. My Froot. Ruby asked, when do we do this? Do this part first. Part first, exactly. Do this part first, because this will give you all the information, the orbital shell diagram, such that you need in the other part. So get this part done, work with your partner, and then when you're ready to move on, then you're going to start moving on and start to build these. So you got a few minutes. Work with a partner, for sure. There's your Froot Loops back. Okay. No, none for you. None for you.
So I'll do a.
I did that, but then I thought I had to drive.
Oh, I see what you're saying. Oh, you just do XX, yeah. No, just do it as it currently stands. Don't do it before and after. So this one right now has 6 dots to it.
So I will put some.
Yeah, but it's opposite.
Yeah.
It's okay. So yes, you would put the 6 dots and know that, oh yeah, it's going to gain 2 more. That's what it's going to do later. But you're just going to draw this for the atoms, not
So
that.
it doesn't matter.
Stop.
They are in the final one. 2 in the first one, 6 in the second one. Oh, correct. It only has 2 energy levels, so it's worth 1. They'll either have 1, 2, or 3 energy levels, depending on
I just
time.
do errands.
Yes. Yes. I'm going to hit stop on this because nobody needs to see this be dead. All right.